Hello and welcome to another episode of Throttle Stop Garage. In today's episode, we're going to have a look at the process that I'm using to design a suspension from scratch. Stay tuned. So in the last video up here, we had a look at the problem that I've got myself into in the project, where the suspension that I was going to put in, this one over here, is for sure not going to work. I'm going to cover some of the details for that because I've got more information now than I had when I filmed that video. But in today's episode, we're going to have a look at the process that I've been in for the last month or so and the rabbit hole that I've hopped down in trying to get a suspension designed from scratch. Not using anyone else's parts, not adapting something from another car into this car. That's not going to work. A lot of the videos that I've found on this subject, and there's a ton of them on YouTube, almost all of them are really super basic. You know, what's camber, what's caster, what's scrub, what... If that's what you're looking for, this is not your video. We're going to be designing a suspension from zero, and we're going to go through the entire process. There's just no other way for me to get this to work, and I can't find all the information that I'm looking for. So this is for people that are building kit cars and other things, or like me, that are trying to design something for a car that just doesn't have an aftermarket. And we're going to go through all the engineering processes to get that done. And what else can I say? I have no desire to do this. I didn't want to do this from the start. I thought somebody else could do this work for me, and it turned out that didn't go very well. So let's just jump in and we'll review what happened over here with this Corvette suspension. Alright, by way of a quick recap, this is the suspension that I was trying to put in the car. It's out of an early C4 Corvette, so 1984 to 87. Now, this Corvette suspension, originally when I purchased it, I didn't have the crossmember. I only just got the crossmember. This is how I found the problem. I had purchased another person's crossmember online, and that was like, I think 10 or 11 years ago, which is a long time ago now. Maybe they fixed their problems. Who knows? I don't care. At the end of the day, this suspension, I was having some issues with it once I got it installed in the car. So I built a frame. Again, have a look at previous videos. I built a frame. I put it in my car. I welded it into that car. And then I just wanted to test it. So I decided I would test the kinematics of it in a static sense in the car. And then I discovered that everything wasn't working the way that I hoped it was supposed to work. But I was trusting that somebody else was going to do my engineering for me. And that's really where we get. This is the road that happens to be paved to a very hot place. So we've got an issue. Now, the original problem was, as I discovered, as soon as I bought the crossmember, because I wanted to validate the geometry here. I didn't want to take the other version of that, knowing that I had an issue. I wanted to validate the geometry using the stock crossmember. Then I was going to shrink everything up on the fancy jig that I built over here. And then I was meant to package this all up, chuck it under the car, and I was going to be done with this months ago. It's been 6 weeks, I think, since the last video, and I've been working solid for that entire time, just reading or playing in the computer. I've not been out in the garage. You don't want to do this. Just start there. I have no desire to do this. You don't want to do this, and hopefully I'll be able to help.
All right, I think the easiest way to start the conversation is to just go over the way that this is done normally. So let's look at the normal process. So here I've got a front model of the Corvette C4 that I've imported into Fusion, which is the CAD software that I use. And in that software, we're going to begin by extracting all of the pickup points for the suspension. Now, before anybody goes and comments about the upper control arm and the side view and all the rest of that stuff, don't worry. I've done all of that in reality because I do have the suspension to check. So once you've pulled all the pickup points, you've got the track of the car, as you can see on the bottom, and you've got all of these bits of data. You can then switch over and go into a suspension analysis software. In this case, I'm just going to use a very simple online website. No sponsorship again involved here, but Racing Aspirations is who I've been using for this. And I'll be using some other software that can perform the calculations in 3 dimensions and allow optimization and do other fancy things as we move along. All right, so now so those points have been taken and imported into racing aspirations, and they instantly give us a few things if you pay them just a few dollars. It doesn't cost very much, really, quite economical. But they then will give you a roll center location. You have the ability to input the parameters by dragging points around in the interface, which I find a little clumsy. But if you're interested and you do have the data points, you can just type them into an editor, and in they go. And then you can do things like start to understand how the suspension actually moves if you want to articulate it. And it's pretty good actually for doing things like simple roll analysis. So you can get most of the basics done right here. Now, this is what most people do. Get your suspension, drop it into the calculator, figure out a roll center, make some very small modifications, and then figure out where you're going. This isn't how we design things, but it is how we do a little bit of learning. Here I've highlighted that roll center, and you'll notice that there's a tan area underneath it there that's in a kind of parallelogram. That describes the space over which the roll center will migrate if you're moving the wheels. So if you move any one of the wheels up and down, or you roll the car in either direction, you'll notice the roll center will migrate within that triangle. So in the Corvette C4 case, you'll notice that the triangle is asymmetrical. So it's wider at the front than it is at the back, which means that as we go up into bump, it's going to migrate more than if we go into droop. And the space is pretty large over which that roll center will travel, which is also an undesirable property. So base level analysis, when things go green in racing aspirations, you're good. You can also perform some basic roll. So in this case, I'm applying a roll to the suspension, and you can get a plot, a graph of that particular motion and see what it does. I can then compare it to what happens in the garage, which is really nice. And let's have a look at what happens here in this roll. So in roll, you can see that we've got one tire, again, in the direction of the roll. So the way that the arrow in the middle is pointing, then that's the tire that's going to be compressing, and the other one is going to be extending. So I've just got the blue arrow showing you the direction of tire motion. So as you roll, one's basically going up, the other one's coming down in order to stay in contact with the ground surface. That's important because through that motion, we can start to understand what's going on at the contact patch. At the contact patch, you can see that as we've rolled, in this case, to the left, the contact that the tire is making with the ground is decreasing. So the red arrows that have just popped up show that decrease in contact patch area. So you'd like to maintain that as flat as possible as you can as you're articulating your suspension. In this case, we're losing contact patches on both sides in roll. So this is going to be a sort of slippery situation. You can also see the roll center migration. So in that case, in the roll, it's just moving laterally to the right. And of course, it wouldn't be any fun unless I could show you this in some sort of an animated way. So here I can show you a single wheel bump and how that roll center moves. And I can grab that center and give it roll and then see how that contact patch is decreasing as we go. So a very useful tool.
All right, first and foremost, the most important thing to remember whenever you're doing suspension design is it's all about the tire. It's all actually about the contact patch, which is an area about the size of your hand that sits on the ground. Well, I guess depending on the size of the tires. So we need to start here. This is our first starting position. You need to absolutely know what the track is. So that's the center of the tire to the center of the tire, right? And you need to know the outside to outside, and then I'm going to use the size of the tire that I'm going to use in order to calculate the track, because this is just a tire I have lying around in the garage. I'm not actually putting a 245 on the front of this car. So I'm going to get my tape measure out. I've got a tire on the other side. This has to be reasonably precise because we need to get all of this stuff stuffed up underneath the fender and still have a reasonable amount of room. So the car's set at ride height right now on the jig that's on the ground. And I've got the tire, again, just mocked up. It's the right height. All right, that's about it. But you need this measurement. So we're going to go Okay, so I've got my tape measure hooked on the edge of the tire. I've got everything set here the way I want it. And when I string it over, what I'm getting is 1,520 millimeters to the outside, right? So then I can take the width of the tire that I'm using, I'll take that away from the total, and that's going to give me the track. That'll be wheel center or tire center to tire center. I need that measurement almost more than any other. Okay, the next piece of the puzzle after you have the track width set is you got to figure out a steering rack. Okay, so you're going to need to have the thing go around corners. And based on the track, you can start working out some of the details, but you can't work out all of the details. You still have way too many variables, and we need to start pinning the variables down. This is key to this design process, is actually getting those variables known. So I've selected this steering rack. I'd purchased a very fancy steering rack for the Corvette thing. Again, one day that'll show up on eBay. But this rack is a standard rack that comes out of a BMW Z3. Early 2000s, late 90s, early 2000s. It's 2.87 turns lock to lock. They're about $300 all day long, and they're around 610 millimeters from pivot to pivot. So we do need to get that measurement. The other things I like about this rack, it's compact. It has a simple attachment mechanism. Again, a couple of tabs here, right, on that boss and this boss are going to get you figured out in terms of holding it. It's reasonably compact, and it's available in the marketplace all day long, and it's, you know, it's pretty good. So let's have a look. I mean, again, when I bought it, it came with boots. I've just pulled them off for this exercise. So let's have a look at getting these measured. So if you've never had to do this before, and I certainly haven't done it very often, all you do, you have to figure out where the pivot is. There's a ball in here somewhere. I can take all this apart, but that starts to sound like work. You don't have to do that. Now, because it's brand new, it's pretty tight. I cant it all the way over one side. It's as far over as it'll go. And then I'm going to take my ruler. I'm going to put that ruler as straight as I can along this, and I'm going to try to hit the middle. Now I've got some features here that are helping. All right, so I've got a feature in here that's helping me sort of track middle. I'll get the right pencil out. And I'm just sighting it, like doing this by eye. Actually, it's more accurate than you think. It's about as accurate as it can be. So I'm looking along the threads, looking along the shaft, draw a line. Then I'm going to take it as carefully as I can. I'm going to shift that sucker all the way over to the other side, trying not to rotate it. Back to the same trick. And this is where that ball intersects. Right there. Okay, I'm going to do this again on the other side, and then we're going to take a measurement. Then the only way I can do this, because it's what I have, is I have to do this with this thing not flopping around on me. I have to do this with a tape measure. If you need to double check it, just double check it. So I erased my marks, I flipped it over, I'm double checking it. This way is easier actually, because I don't have to deal with all of this junk. So I'm going to hold it there, tape there, and I'm out. I'm 615. Okay? So you got to write these numbers down. I use a book. So 615 millimeters is what you have for your steering rack pivots.
Then take the measurements and put them all in the computer.
Next, hubs. All right, I need a front hub. I wanted it to be modular, so I've selected a Nissan 350Z hub. This is the cheapest hub that I could buy. I also have, I purchased a Nissan 350Z front upright because I wanted to know how things were oriented with respect to the bolt holes and everything else. So I bought that just on spec because I needed it, or at least I think it's a good idea to have it. So this isn't going to be a part that I'm using. I'm going to use the fancier SKF brand one. I just wanted to see what the difference was between a $30 one and a much more expensive one. It turns out there's some critical differences, a little thinner, just a little looser. Anyway, it's fine. So this will work for mock-up purposes. The other ones will be the real ones, but we're going to talk more about that in a sec. The next thing are ball joints. These are pretty... I picked some standard products. I didn't want to take any chances here on buying things that are weird. So this is the standard screw-in ball joint. It actually came from, I think, 1950s Chrysler products, of all things. This is the Moog Problem Solver. You can find these almost anywhere. So they're easy to get a hold of. And then their screw-in, they'll be more than adequate for this application. And they screw into a sleeve that I can buy off the shelf. So that's a good thing. We can screw them in. We can build arms around that. The problem with these, there's no problem with these really. You have to do that same trick to locate where the center of that ball is, because we need to know that spot. Now, I'm not going to use these parts. These, again, they're cheap, they're cheerful. If I ever ended up in the middle of nowhere and I needed a ball joint, I can get that ball joint. They're also used extensively in sort of NASCAR style racing stuff, short track and other things. These are the very much nicer versions of the same part. Just have the upper and lower, so I'll show you the same. So this is a Howe Racing. Again, no anything on these, but oh, that's nice. Okay, so that's the Howe Racing product. It's the same thing. I did buy the ones with the steel caps. They still screw in. They still are, again, this part and this part are in essence the same. The ball location is going to be ever so slightly different. So I'm going to engineer around the part I'm going to use. That part's just there for build purposes. You'll see why I bought that later. Just notice the beauty of these ball joints. They're absolutely stunning. Now, these are for racing only, but they're fine on the street. I mean, seriously. Just, lubricate your ball joints. That's why you have a grease nipple. They don't have any of the sort of slots and other things that this has to carry grease around in them. So you do have to pay attention to them, but we all pay attention to our cars anyways, right? So this is no big deal. They're very low friction. I've never heard of anyone ever wearing out a cup. You can wear out the pin, but the pins are really tightly controlled dimensionally, and I have the drawings for those, and I do not even have to take these apart. They're perfect. So with all of these parts, the suspension now moves out of the shop and into the computer. I don't mind telling you, this takes me an awfully long time to do. Here I am back in Fusion. I've now got everything modeled, so you have to model every single part. So I've got the brake that I'm going to use, the mount for the brake, the hat for the brake rotor, here's the ball joint modeled. I literally modeled everything. It took, I don't know, like a long time, but now that I'm done that, we can move on. All right, so as we kick off into the computer stuff, don't forget, please like, subscribe, and comment below. It does help the channel out. Right off the bat, I gotta say a few things. First, you're going to have to read. You're going to have to get all the books, read all the books. You're probably going to come back to race car vehicle dynamics. This is the big Bible for the SAE and how to do race car dynamic things. But it's not necessarily a great read. So chapter 17 is really where you need to look into. That's the suspension geometry chapter, and that lays out most of this. What I found is a bit inconsistent and a bit difficult to follow is a lot of the suspension analysis that gets done is on pre-existing suspension geometry. If you're designing your own suspension geometry, a lot of the former inputs become outputs. So I'm going to talk about that now. So we're going to start with the basic tire model. So we've got a tire here, a wheel, and I've put the wheel face in. And again, you're going to have to figure out offset. So we have a negative offset here. And we're going to start designing from this point. Now, the first reference point that you need, so back in the garage, we took the track of the vehicle, so we know the track.
And once we've got the track set, the next thing that we need to actually set is the scrub radius. So that's step 2, scrub radius. Put the scrub radius in. If you don't put the scrub radius in, you'll chase your tail forever. All right, so the next question that always gets asked is how much? How much of these parameters is too much? Well, we know from that Corvette C4 that 74 millimeters is an awful lot of scrub. So we're going to lower that. And as a viewer suggested, we're just going to look at some cars that I can find the reported figures for. And I found that most cars that are reasonably handling sports cars are between 10 and 15 millimeters of scrub. So I set 10 to 15 millimeters of scrub. And I decided, hey, it's good enough for now. What I can tell you is if you don't set the scrub now, you can't hope to get it right later because the scrub governs the next suspension parameter, which is the steering axis inclination. Now, the reason you need the scrub first is the scrub defines where the steering axis inclination hits the ground, right? So that's just the steering axis and it's inclined. It tends to run around 10-ish degrees. So we're going to set it up at around 10 degrees. And if we don't do that first, I found it was just about impossible. Again, you're chasing your tail. So this is inputs becoming outputs. This is a needed input. You need to know what that steering axis inclination is. And you need the scrub because it describes that line that's sitting right there. All right, so once you've got the steering axis inclination set, you need some points to define that line in reality, and those points are actually your ball joints. So your ball joints are going to set that steering axis inclination for you, and this is where you're going to encounter your first problem. So now that we've got the ball joints installed, in essence, we have to go back to the CAD model and check to make sure that we're going to be okay, and especially the lower ball joint. You have to check that the lower ball joint isn't going to hit anything. At this point, I haven't added in the rest of the junk that gets in the way in the wheel, so let's put that in now. So it's at this point that you're going to start to understand if you're going to be all right. So this is why we had to go into the CAD model first to put all the brake hats, the hubs, the brake rotors and calipers and every other thing in there so that we can get some really simple measurements as we go back out to the suspension analysis software and start trying to place these points in space. Okay, so in essence, as soon as you've got it rectified so that your lower ball joint and upper ball joint will not foul any of the parts, and that includes the size of their mounts, and give yourself a finger's width worth of clearance, 10 millimeters all the way around would be nice. Then if you've got that established, and there is a place within the wheel where you can package this stuff, then you're pretty much set for the next step. Next up, we're going to add in the frame. So there I've added in the frame segment. And then we're just going to slide things around a little bit so we can see them better, but we need a center line and we need a few other things to make the model work. So with the frame and the center line of the car in place, I can now establish where the center of gravity is. This is a rough approximation, but it's going to be close enough. Now, we don't desperately need a center of gravity here as we're designing, but it is helpful for when we go to do some of the other suspension parts that involve springs and other things. So we'd best at least get a first approximation of where it might be. So I have some calculations that I did and I plunked it in. The next variable might surprise you. Of all the points that confused me in the process of learning how to do this, roll center height was probably the first one. And it's the one where the dam broke. So as soon as I learned that roll center height is an input, not an output, the rest of the suspension design is actually pretty straightforward, and I hate to admit it, but hey, that's why we're here. So roll center height, if you're analyzing a suspension, it's an output. If you're designing a suspension, it has to be an input. If you don't have it as an input, again, you're just randomly doing things. Now, once you've established a reasonable roll center, so if you've got your center of gravity and you've got your roll center height, you don't want those two things at the same point. There's jacking forces and all kinds of other things. Remember the reading that I said you had to do. You can set that roll center up. So in this case, again, I went back, I analyzed a bunch of other suspensions. I found somewhere around 60 millimeters seems to be a pretty good roll center height for a lot of cars. And this establishes some real fundamentals. So if you have to change anything, you'll have to go all the way back to here. But 60 millimeters it is, and let's carry on from there. Well, the next question that has to get asked is, where are the instant centers? Once we have a line from the center of the contact patch through the roll center height, we now have the line upon which the instant centers must reside. So for that static position, the only place that you can get all of those geometries to work is going to be with an instant center that passes through the roll center height and hits the contact patch at that point. Trust me, this is easier than it looks, and it's certainly easier than it is to explain. Perhaps this is why I've not seen it explained very well. Hopefully I'm doing a better job. It takes 2 points to make a line, and the next point that we have to add in to get this to work is the lower control arm pivot point that's inboard on the chassis. So you have to define that point. For the most part, the lower control arm does sit at the same height as the lower ball joint. So that pivot point can be placed there initially. If you need to move it around a little later, at least it gets you started. Again, we're designing from zero here. So we've got a chassis. I see I can put a point in there to have the lower control arm pivot on. So we're going to add that point in, and then we're going to keep going from there, because now we get to define another line. You'll notice the intersection point for that line has fallen off our screen, so we're going to reset the drawing and then finish the construction from here. All right, now the last thing you have to do is just go from that intersection point where the red dot is shown there, and you just draw a line right back up to the upper ball joint. In this case, it passes through the frame, but that's not really going to be a problem. Now, the one thing to remember here is this establishes the basic geometries. It doesn't control everything that we're going to have a look at, but it does control where things are positioned at a static ride height. Now, if you're still following along at this point, this took me a long time to figure out and to clarify it to the point where I think I can tell you how this works. So there's one last point to go, so just stick it out. As we needed to define the lower control arm from ball joint to pivot in order to set up and find the instant center, now all we have to do once that line is described from the instant center back to the upper ball joint is we need to place a position along that line that describes the length of the upper control arm. Now, this isn't rocket science, but it sure was for me. After you get this done, you can now position the length of those upper and lower control arms anywhere you like along that line, anywhere, and the geometries will be the same. That's crazy, but it's also true. Now that I've defined both the upper and the lower control arms, then the last thing that you need to know is the relative length of the upper control arm to the lower control arm. That controls the rate of camber gain for your suspension. So if you want more or less camber gain, you can have the relative ratio of those two arm lengths can change to get whatever camber gain you'd like. As long as they're sitting on that line, everything else geometrically will remain the same, right? So the instant center will be the same, the roll center will be the roll center height will be the same, the scrub radius will be the same, all of those things will be the same. Then all you need is to say, what camber gain do I want? All right, we'll tell you how we figured that out. When I worked out the camber curve, I went back to the same collection of cars that I was analyzing, and I found that about 0.6 of a degree per inch, or about a quarter of a degree over 10 millimeters, seems to be a pretty happy rate for a camber curve. Now, in this case, that has to do with relative body roll. I also have to match it to what I have in the rear end of the car. And actually, all the calculations, this is what came out. And as soon as I got that calculation done, then I set the ratio of the arms, so the upper control arm length to the lower control arm length, in order to achieve that rate. All right, so this is the finished suspension. Yay, we finally got there. Well, finished. Let's hold on there. We're not exactly finished this process. We're getting close. So this is what I've been doing. So this is back in Fusion. So I've got all the same principles that I've just illustrated for you, and I've doodled them up in Fusion. That's what I'm using to do this. I've got the frame member and all the other dimensions put in. I've added in a few other lines, like you have to put in not just the point for the ball joints, but the size of that ball joint holder, or the cup that it mounts into. That has to be there. That's a constraint. And to be honest, I kept running into the brake rotor with it. So I've got all the parts listed. You've seen the CAD drawings, so we've got those all spaced back. Then I've got all the points put in where I'm going to have minimally a 1/4 inch, so 6 mil worth of clearance. I was trying for 10, so I have both the hard stop and I have the clearance stop applied as lines. And then I'm iterating back to racing aspirations just to do a simple 2D front view analysis of that suspension. And if I find that, I don't have the parameters I want, so I went with about 12 degrees worth of steering axis inclination. I have about 16 millimeters worth of scrub. I have a roll center height of 60 millimeters in this model. And once I've got all those parts in, then I go back to the CAD model. I go back to racing aspirations, back and forth and back and forth and back and forth. I would also say that this is just my first cut. I still have to do the side view, as I've just said, but I also will have to optimize this, and this simple online software is not going to be enough to do that properly. So we'll be breaking that out, getting the side view done, putting into a 3-dimensional analysis software, and then looking for some optimization for this. So it's not perfect just yet, but it is pretty good.
Okay, that's a wrap for the front view suspension design. It's been a heck of a long time to get that done. Sorry for that. I go as fast as I can, but by the time I had to figure it out, and I did have to wait for it to sort of come very clear in my mind before I could actually get the design finalized. I did spend weeks just going in circles, not too sure what to do, not too sure where to start. So I hope that this video has been some help in providing a little bit of insight into how we get the front view defined if we're designing a suspension. We're going to now turn to the side view for the next video, and we'll start building this. And by the way, if you're a suspension designer or you've got experience in this, please, in the comments below, I need all the feedback I can get here. So I'm trying to do something that I've never done before and I don't have any experience in. And to say it makes me a little nervous, like, car companies spend millions of dollars trying to get this done. So to think that I can do it in my garage without a lot of help is a little bit of hubris. So please, if you can, let's get some comments going down below. I'd really appreciate whatever insight you have. With that said, that's enough for this video. Stay tuned for the next one. And don't forget, keep your stick on the ice.